A few years ago, when I was consulting a wealth management firm, we built what we thought was a state-of-the-art retrieval augmented generation pipeline. It was supposed to read the financial report and answer analytic questions. During a massive demo to the partners, an analyst asked for company revenue. The model confidently generated a beautiful, highly articulated paragraph, and it cited its source perfectly. There was just one problem. It pulled the revenue from 2023 instead of 2024. So the partner didn't care that the language was fluent, they didn't care that the vector retrieval was mathematically elegant. In finance, a temporal shift or a misplaced minus sign doesn't reduce the model reliability, it completely eliminates it. I call this 99% trap. If your AI is 99% accurate at writing poetry, it is a miracle. If your AI is 99% accurate at accounting, it's a liability. If you've been building AI system for a while, you know exactly what I'm talking about. We are trying to force the probabilistic machines, LLM that just guess the next likely token, to do some deterministic jobs. Recently, we published a new paper called Neuro-Symbolic Financial Reasoning that directly tries to offer a real cure for this. It introduced the architecture called VeNRA, and in this video, I'm gonna talk about 4 mind-blowing takeaways from this paper that will completely change how you will build AI agent, especially if you're dealing with some structured data, database, or high stake reasoning. So without further ado, let's jump right into it. Welcome everyone to our channel, AI Fun Fact for All. For those of you who are in this channel, my name is VeNRA. I have a PhD in computer science, and in this channel we talk about AI and machine learning and how we can use it in order to improve our efficiency. As we mentioned, we are targeting one of the main issues persistent in large language models, which is the hallucination, more specifically in reasoning complex tasks that requires retrieving and generating numbers. The first takeaway that I want to talk about is the vector illusion. When we build a RAG system, we rely heavily on vector embeddings to find the relevant information. But the paper highlights a massive flaw called the distribution semantic conflation. Because LLM learns by looking at the context words appear, they group mathematic opposite terms together. Think about a phrase like net income versus net losses. So to human accounting, these are totally opposite terms. But for an embedding model, net income, net sale, net loss, they show up exactly in the same type of sentences, in the same exact document. So they ended up sitting right next to each other in a vector space. So when the user searches for net sale, your database retrieves net income. The LLM anchors on the wrong number and it confidently feeds you, the user, with the total lie. So the takeaway here is that you cannot rely solely on semantic search in deterministic domains. You have to combine it with some strict old school lexical filters, literally gating the information to ensure the exact keywords overlap before it reaches the LLM. Takeaway number 2, the context paradox. This is the most counterintuitive finding of the entire paper. We ran an experiment where we upgraded the retrieval system so the LLM was getting much better and more accurate evidence from the document. So you would assume that the model performance went up, right? Wrong. The performance actually dropped. When the LLM was confronted with denser, more complex tables and highly enriched context, it got overwhelmed. So it experienced a massive spike in generation failure. Think of it as a chef. If you give a chef 3 ingredients, they can make a decent meal. If you dump 1,000 ingredients in one center, they freeze up and burn the kitchen down. So better evidence does absolutely nothing if your generation mechanism can't absorb it. You can think of it as the context rod problem. So what is the fix? So stop using the LLM as a calculator. The paper advocates for cognitive offense offloading. So let the LLM be the architecture that write the step-by-step logic plan, but hand the actual math and the execution over to a deterministic Python environment. Takeaway number 3 is a terrifying phenomenon called the semantic drift blind spot. So we tested the world's absolute best frontier model. We're talking about the open models like Llama 3 70B and the closed ones like Gemini 3 Flash on their ability to catch subtle financial errors. 5 of these massive models scored literally 0 on the semantic drift. So what is semantic drift? Semantic drift is when a model swaps a highly specific entity with a plausible synonym. For instance, swapping operating income with operating profit to a language model that looks completely fine. As we said in the takeaway number 1, it passes every linguistic vibe check, but for a SEC, that's a completely different taxonomy. The models are entirely blind to this because their training forcing them to look at the broader narrative coherence, not strict ontological boundaries. To fix this, you have to realize that generating reasoning cannot recover these lost nuances. You need to have a strict schema-driven classification before you ever generate a word. This kind of brings us to the takeaway number 4, how we actually teach the model to catch these errors. Right now, if you want to train an AI to detect hallucination, you use a benchmark whether another LLM was prompted to write a lie. The paper actually called them swarm and hallucination. They are actually lazy, obvious lies, but in real world, AI doesn't lie like that. Real production failures are mechanical. It's a column shift in a table, it's pulling a number from 2022 instead of 2023. So we stop asking LLMs to generate lies. Instead, we build a sabotage engine. We took perfectly correct data and programmatically deterministically mutated. We shifted a matrix by 1 column. We swap a valid input variable for a distractor. This is like the difference between showing an AI a cartoon of drawing fire versus running a highly stressful randomized fire drill. By training our Sentinel detection model on this precise mechanical sabotage, we built a system that caught 93% of the error, operating 53 times faster than standard reasoning models by just giving it 1 token inference time. So let's bring this all back to the catastrophic demo I had years ago I talked earlier. If I had known it back then, I wouldn't have tried to fix the problem by just a bigger LLM or expanding my context window. Scaling doesn't fix the architecture mismatch, it just delay them. If you want to build a system that can actually trust in real world, you have to embrace neuro-symbolic design. Use the LLM for its linguistic brilliance, but lock it inside a deterministic cage to extract the exact verification and code execution. I would love to hear your take on this. Are you still using purely vector searches, or are you starting to inject deterministic code execution and extraction in your pipeline? If you enjoyed the video, make sure to like it and let me know in the comment if you want me to create another one going over the actual code and show you the demo. If you enjoyed the video, I think you also like this one that I talk about how you can give the history of the LLM previous results in order to improve its performance, or you can watch this one that I talk about the extraction using the Google language stack and how it actually try to solve the LLM hallucination. Thanks for watching and see you until the next one.